We've been doing space research for about 20 years now, usually on kind of big, species expanding topics like space elevators, space-based solar power, space stations, all the kind of big, dreamy science fiction-y projects. Those are the kinds of things we tend to work on. During the pandemic, to kind of stay in business and stay alive, we did this very surprising pivot into media. We hosted 27 virtual conferences like this for various organizations. I think eight different organizations. That was our honor and privilege to do that. They were terrific clients. But then as the pandemic shifted gears again, we have recently started building a podcast network. So we're pretty happy about that. This show, the Dare Greatly show, is a part of our branding for Better Futures. Better Futures is going to become a subsidiary of Liftport Group. So it kind of lives on its own as we get back into the main work of working on the elevator. And we're pretty happy. We've got the Mars Society as one of our clients. They're going to do a show, I believe it's next week on Tuesday. I'll have to check the dates. We've got some great guests coming in. We've got Dr. Gordon Ressler coming in next week, I think on Monday. He's going to talk about robots in space. You're definitely going to want to pay attention to that. For anybody who pays attention to the policy work that we do, he's been really involved with some really important documents. Robotics in space, refueling in space. His time as a program manager at DARPA is fascinating. I am really looking forward to it. I don't really know him very well, so I'm looking forward to learning a lot during this conversation. So that's going to be terrific. One of the genuine catalysts in our field is going to join Red Planet Live with the Mars Society on the 21st. Rick Tomlinson. Tomlinson started the Space Frontier Foundation, the Earthlight Foundation. He was instrumental in creating Planetary Resources, one of the first pioneering asteroid mining companies. And now he runs Space Fund. So he's going to be a terrific guest on Red Planet Live. That's the Mars Society show. We've got some other stuff in the works I can't talk about yet, but I'm pretty happy about it. And with that, I just want to say to everybody who's kind of been following along, thanks for joining our journey with us. We're going to host a conference, DareGreatly Space at the end of March. We're pretty excited about that. We have some cool news. There's some stuff we're going to share that you're probably not going to get anywhere else. So pretty excited about that. It's still definitely a work in progress, but yeah, I think you're gonna like that. So this show is really about the intersection of space, commercialization, policy, all of those things that kind of make this new effort that humanity is taking to move to space. That's what it's all about. We're going to switch gears a little bit today because after talking to some of our fans, after reading some of the comments from the shows, we realize that there's a pretty big disconnect for some people. They want to talk about the business. They want to talk about all the science fiction, all the big ideas. That's all terrific. But one of the things that space businesses need is a really thorough grounding in physics. So we're going to be talking with Professor Stephen Cohen. I'm going to bring him on in a minute and read his bio. So we're going to talk about the physics of space. And I don't know anything about physics. Stephen and I have laughed about my lack of knowledge for quite a while now. So I'm going to ask some pretty basic questions, I think, because I want people to understand. I think it's important that people understand that while other businesses, if you've got a yoga studio or lemonade stand, yeah, you've got to deal with basic market forces, but they don't usually have to deal with forces of the universe. So we're gonna talk about that. So let me bring in Stephen.
I'm behind
Yep,
a book.
I see that. I'm gonna change that and do that and put the book back. There we go. I'm gonna actually make an error in your school. How do you pronounce the school? It's
Vanier.
French.
Vanier College.
It's Vanier, French.
Vanier College, yeah.
Okay, all right. Stephen Cohen, a physics teacher, has published Getting Physics, Nature's Law as a Guide to Life. This book aims to introduce physics concepts without resorting to much math, so anyone can enjoy it. Yes. Storytelling and humor make topics like mechanics and electricity fun to read about, while metaphors offer a deeper appreciation for the content. Although the chapters on physics are written with college students in mind, ideally suited to be integrated into pre-reading for introductory courses, chapters on engineering, aerospace, and future technologies are lighter. Stephen Cohen will donate 1/2 of all profits derived from sales of the book to charities that support student education. Getting Physics, Nature's Law as a Guide to Life is available on Amazon. And I'm going to post that link here in a moment. Stephen Cohen is the co-recipient of the National Ken Spencer Award for Innovation in Teaching and Learning. He is the author of a new book, Getting Physics, Nature's Law as a Guide to Life. He obtained his bachelor's and master's degree in mechanical engineering at McGill University. Yes, excellent. He published the first ever comprehensive analysis of the mechanics of space elevators. Also awesome. That's how we know each other. He has industry experience designing space payloads and has spent more than a decade teaching the fundamentals of physics. And with that, it is a pleasure to bring you on, sir. I'm really excited to kind of
Happy to be here.
dig into this. Yeah, terrific. So this isn't going to be a talk on space elevators. I promise you that. That's not where we're going. I do want to give a little bit of context that is kind of how we originally met while you were still a grad student. I'm going to post the links to your book, but also in the chat, post the links to the Scientific America article that you just just got a lot of attention on. So Steve and I were trying to figure out like just how long ago we met. It's measured in north of a decade. Hold on, here we go. Here is his book, and we'll post this again because. Well, that is curious.
Oh, no. You know what? Maybe don't put that link on.
Okay.
Oh yeah, no, that's okay. It's telling me I bought the book, but I know that. I just checked the link. I was like, is it good? But I'm sure it's fine. It won't say you bought the book when you go there. Okay, perfect. Sorry about that.
Okay. Leah, I am having technical difficulties to activate the chat, so it is not letting me link that. Thank you. You'll do it. Thank you. I appreciate that. So we started talking probably in the neighborhood of, could it be 15, 16 years, 14 years?
It was definitely 2009 Space Elevator Conference in Seattle. That's right. Where we met.
Okay. So, and everybody else, that I moved away from working on the space elevator. That was a pretty significant shift for me. Still believe in the idea. I just think it is still very work. That I will 100% attest to. I am much more concerned about the economics. I question, and I really question rights of way and law and policy that are going to get in the way of that thing. But that's not what we're going to talk about today. Let's talk about what you're doing. First of all, let's have some background, a little bit about some of the stuff that your students see when you're in class, and then what made you decide to do this book. Like we'll come back to space in a minute, but I want you to kind of give people kind of a background on who you are, where you come from, why you do what you do.
Sure. Okay. So I guess it was 2006 when I published my master's thesis called The Dynamics of a Space Elevator. And then I looked for an engineering job, and I worked at MDA Space. If I had to make a comparison, it's like the JPL for Canada.
Right.
So they're making not spacecrafts, but payloads for space. And the robot arm, Canadarm, came from them, and so on. Anyway, so I worked there for a few years, and funny thing, great job, but after you've worked with space elevators for a long time and you're thinking out of the box a lot, you build traditional satellites and components and reflectors and the regular stuff, and I learned a ton. It's an awesome engineering job, but after a couple of years, I was like, I want to go play in the sandbox again. Okay. So ever since 2010, I've been at Vanier College, and when I'm not teaching, I sometimes am dabbling in space elevator dynamics research, and but there's no requirement. It's not a university where research is a requirement. So I do it when I want to do it, but it also leaves opportunities for other things. So I started a blog actually in 2010 that I brought into my classroom. Basically, I would write stuff and students would read to get ready for the content we were going to learn about. And I would write without math. So they'd learn concepts, and then we get to class, and now we add the rigor. And over time, the bank of things I wrote on my blog grew, and I took the best of it and then saw what gaps were missing, and I piled it all together, and that's the book, basically. Nice. So the book is something I use in my classroom. Only the harder, let's say, 4 chapters in it are what I use in the classroom. The rest of it's lighter reading, but if you can get through those physics chapters, then you have the basic concepts that college students should have in physics.
I was having a conversation just this afternoon about mission designs and requirements and trade studies and trade spaces. And throughout that whole thing, you've got ISP, specific impulse, you've got delta V, rate of change. Let's talk about orbit. Let's talk about what it takes to get from the ground to orbit. Just the first problem in space, right?
Well, I think you have to start with what really an orbit is.
Okay.
I think a lot of people think that when something's flying in orbit, it's using fuel. That might be a misconception a lot of people have, because it's moving very fast.
Right.
If you're in low Earth orbit, like the International Space Station, you're moving about 8 kilometers every second. So it's a huge distance in 1 second, just to try to imagine.
Yeah.
Okay.
Yeah.
So how do you get that speed is really the challenge of space. But why do you need to be going so fast? Well, if you just dropped something, so here's Earth, here's Earth, and now I'm in low Earth orbit. Like low Earth orbit is pretty close to the surface.
Yeah.
But no matter where along here I would just let go of something with no speed, it would fall and hit the Earth. Nothing surprising there. But you notice whenever you throw something, it's now in orbit. Even a ball, when a baseball player throws a baseball, the ball is in orbit for a very short time. But that orbit is going to coincide with the surface of Earth eventually. And so it won't be a continuous orbit. It'll be suborbital.
Okay.
right?
Yep.
Yeah. But if you really want to be in orbit, you need to throw that baseball so hard that, yes, gravity will cause it to bend, but the Earth is curved, fortunately, and so it bends, but at the same rate at which the Earth is curved, it'll never touch it. Except that on Earth, we have the problem of atmosphere. So take that away, which is what happens when you get just outside the atmosphere, and now you have something in orbit. Now, if it's moving too fast, it may continue going, even though Earth's causing it to change direction, it could eventually leave Earth's sphere of influence. So there are different kinds of motion going on around planets, but the kind to really wrap one's head around, I think, are just the circular and elliptical orbits that happen. And what achieves a given orbit is, well, what altitude are you at? And assuming at one point your motions, okay, so here's a line joining, Earth to my satellite. And if I'm moving, let's say, perpendicular to that line, there's really only one speed that'll keep me in a circular path. If I have any other speed, I'll be in some kind of elliptical path,
Right.
or I'll go so fast, that I escape.
And that's 8 kilometers a second. That's the magic number.
Well, that's the magic number at low Earth orbit. It turns
Right.
out to stay in orbit at higher altitudes, you don't need to go as fast.
Right.
Okay. So here,
which to me is boggling. That is
it is a bit strange. It's a bit counterintuitive, but it has to do with gravity being less the further out you go.
Talk about that.
Okay. Yeah. Good.
Yeah.
So Newton discovered, well, his story is just mind-blowing. Probably the most amazing story in all of science. So good place to start our conversation. So in the late 1600s, Galileo by then has discovered that these planets go around Earth in ellipses, not circles. And that was surprising to people. Also the fact that the Earth would go around the sun in ellipses, not circles.
Yeah.
I mean, just that it would go around the sun at all.
Anyway, at all. Right.
Get away from that. So, and Kepler then was working on understanding orbital mechanics and saw certain relationships that, the area swept by an orbit in a certain amount of time would be the same at another amount of time. So if in a month here, you sweep the same area as a month here, even if it's an elliptical path. So not an obvious thing, but we still don't have a law of science yet. Newton's the first to say, okay, what ground rules does the universe work with? What are the rules here? And he discovered two of them really in figuring out what makes these elliptical orbits. First, he had to invent calculus.
Right. No small feat.
Whole, branch of math.
Only math, right?
Yeah. And then use that calculus in conjunction with two laws he proposed. And then it seemed to check out. Basically, the two laws, one being universal gravitation, and the other being the second law of motion that we know as how forces lead to acceleration. It's a very complex problem. I really saw it in its proper mathematical sense, I'd say third year of university.
Okay.
So it takes time to develop its vector calculus. It's not easy stuff. And anyway, but the laws themselves are not that complex. And so gravity, one of the laws I was mentioning, basically says that all mass pulls on all mass.
Right.
So Earth is a giant mass. The more mass you have, the more you pull. But, my two fists, I can't seem to get the right to left right.
Yeah.
My two fists are currently pulling on each other, but it's inconsequential. It's negligible how much they pull because they're small masses. Now, the closer things are together, the more they pull. And that's important because it's a square relationship. So if you are 1 Earth radius away, okay.
Yep.
So the center of Earth being the center of my fist here.
Center of mass. Yep.
Yeah. So if I'm a certain distance now away from the center of mass, if I double how far I am from the center of Earth, so I double, I actually am 4 times less pulled by gravity.
And that's the inverse square law, right?
That is right.
Okay. See, I'm not totally lost here, but this is so 1/4 the gravity at
Twice as far away.
Twice as far away. Yeah.
Yeah.
Yeah. I have been trying to explain the Lagrange point, Earth Moon Lagrange point, for a while now, and even people that are pretty close to us, on this project, they keep trying to refer to it as null gravity, and I keep trying to tell them there's no spot where there's no gravity, but you have balancing forces. Yeah. So can you take your inverse square? Can you take your distance from the Earth, and then really kind of like tie into how does the Lagrange point work?
Okay. Well, so it actually requires, we talk about that second law that Newton, that really went into understanding how orbits work back in the late 1600s. So like I said, he combined universal gravitation with what's called the second law of motion. It's funny, the second law of motion is probably the most important equation for most of us in terms of understanding day-to-day life. Yet most people say the most famous equation is Einstein's E equals mc squared. Everyone knows that one.
Yeah, because it's on a t-shirt.
Yeah, it fills a t-shirt. So does second law, by the way. It's a beautiful looking law. It's got a capital epsilon, Greek symbol, then an F with an arrow on it equals M, and then an A with an arrow on it. That's it. It could fit on a t-shirt real nice. It just doesn't have the publicity that E equals mc squared has. So here's the thing.
Not a good enough agent.
No, that's right. The publicist, Newton's publicist, missed that opportunity. So what that law says is that take any mass, and we'll call it M,
okay,
and I can tell you what its acceleration now will be at any instant if you tell me what all the forces are that are acting on it right now. So sum of forces equals mass times acceleration means give me a laundry list of all the forces acting on you and add them up together. Okay, they combine to make something.
Okay,
and that'll be equal to the product of mass and acceleration. My students struggle at first with understanding what acceleration is.
Okay, I'm looking at the formula right now.
Oh, you are
actually, yeah. I don't know if I can put it on screen for a moment.
Okay.
I'm not going to take away from this, but. So it's right here.
Oh boy.
Right.
Yeah, you got to really zoom in to see it, but
oh, you do. Let's it's right here.
Yeah, I don't love that because you're missing the sum of symbol. Anyway, I'll come with my equations next time.
Okay. All right. I'm going to stop sharing because this is good, right? This is good. I'm learning some important stuff here.
So acceleration is the rate of change of velocity. Velocity is not only how fast you're going, but what direction you're going in. Velocity tells you all that. Speed is just how fast you're going. But to really describe, let's say, how a satellite's moving, you need to say how fast it's going and in what direction. If you've said that, you know it's velocity.
Okay.
Now, if it's constant, if something's moving in a straight line with constant speed, that would be constant velocity, zero acceleration is happening. A is zero.
Okay.
And if something's at rest, its v is zero, its velocity is zero, and it's staying at zero, again, acceleration is zero. The only way that those things can happen is if the net force acting on something is zero. It doesn't mean there are no forces acting. Of course, in the universe, you can never really be completely absolved of any force at all.
Right.
At a minimum, you'll be so far away from a big planet or a big star, you'll be so far away that it's very small, the force on you.
Pardon me.
But the only way you can have zero force really is that you have multiple forces and they're canceling each other. Okay. And that is the story for your Lagrange point.
Right.
So you could be somewhere between Earth and Moon. Right and left.
Right, yep.
There must be a place between there where they're both competing for your love. The mass is being pulled both ways. But if you're not at exactly the right point, then it's really an unstable equilibrium. That
right, yeah.
So if you get any closer to Earth, it's going to overwhelm and you'll accelerate towards Earth, any closer to Moon, and the same thing. So that to just stick something at that Lagrange point and think it'll float there, it won't. The slightest, it's called an unstable equilibrium.
Yep.
It's like if you put a ruler, a meter stick, just standing up, the net forces are zero, but the slightest disturbance and it's going to fall over.
So I keep trying to describe how the moon has these perturbations because it's not a perfect orbit. It's an oblong orbit, an oval orbit.
It's elliptical.
Elliptical. And because of that, the Lagrange point is moving moment to moment to moment to moment. So it's not so much a point as a mathematical range of where that place is.
That's right? A good point. Yeah. And of course, it's moving in space. Even if the moon were a circular path of Earth, the Lagrange point would be moving in space as the Earth and moon do their, orbital dance in the solar system.
Right.
But if it was, but it's not circular, so it's slightly more complex. That means the relative distance from Earth or to this point or this point to moon, that relative distance is slightly changing, slowly, but yeah.
Yeah, it's a tricky problem. And the idea of us trying to put a lunar elevator there, it's complicated. That's the simplest thing I'm going to say about it is it's complicated.
Yeah, I think if we're going to do Space 101, we can't go straight there. I think, if we're talking about what an orbit is, if we have a decent idea what that is, still not perfect. So I think we can get back to that and really round it out a little. So we've established you need to have a certain speed so that gravity's pull, it's going to change your direction, but not so quickly so you're not going to hit Earth. You're just going to keep falling around it. Right. If we're in no atmosphere and I threw a baseball out the window and I threw it hard enough, it would hit me on the other side of my head. That's if you're trying to imagine what an orbit is. Now, if you're standing on that baseball, you're weightless. We say, but that doesn't mean there's no weight force acting on you. So being weightless is really more of a sensation. It's feeling like you're falling. So that's what people feel on the International Space Station. So there's this misconception that gravity is zero there.
Right.
It's absolutely not. Gravity there is almost as strong as it is here. They're only 300 kilometers or so or less above the surface of Earth.
Right.
Why are they feeling weightless? It's because they're falling. It's because the centripetal acceleration they feel is really the other side of the sum of forces on them. So yes, there is a net force pulling them down. Why don't they move down? It's because acceleration is not how you're moving. It's how your movement is changing. And that's the complicated part. So a lot of students come in to my class with the idea that acceleration, that velocity is based on what forces are acting on you right now. But that couldn't be more far from the truth.
Wait. Stick with me. Say that again.
A lot
I kind of know some of this stuff, but
okay, sure. So a lot of students have the false impression that the more force you have acting on you, the faster you must be moving. But that is completely untrue.
Okay.
All forces can do is change whatever velocity you have now. And the more net force there is, the quicker your velocity will change.
Okay. And that's delta V?
So when what A is, it's how quickly are you getting that delta V? Okay. Delta V means change in velocity. Now, here's where things get a little tougher for students than that. So they understand, like when you're in a car, you start accelerating. That means you're picking up velocity. It must be forces doing that. They can understand it in one line. But here's the thing. When you're in orbit and you're going around in a circle, you could do it at constant speed, but you're still accelerating. Hold on. How is that possible? Why am I accelerating? You said the speed was constant. If we go back to what acceleration really is, it's the rate of change of velocity. That's not just speed. That encompasses direction.
Direction. Okay. All right. Okay?
So you're in a, let's say you're in a simple orbit, it's circular.
Okay.
You're changing direction. The way your velocity vector is changing, it's actually pointing, the delta V is actually pointing towards the center of Earth. If you look that I had a velocity this way, and soon it's going to change to that way. How did it change? You get a new arrow that points to the center of Earth. That's the direction of your acceleration. Why am I accelerating that way? Because there's only one force acting on me, and it points to the center. So, you know, Newton's equations, they're working. And so just this very concept is the beginning of accessing space.
Brilliant. I definitely learned some stuff on this conversation. All right. So now we know what it takes to get to orbit.
Yeah, you need speed.
You need speed. So how fast? Let's say we want to go to Leo or we want to go to Geo. What are the speeds for those two places?
Oh, I don't have Geo off the top of my head, but it's considerably less.
Yeah.
I could get out a calculator and have an answer pretty quick.
Okay.
Maybe when if you ever send me away and bring me back, it'll take me literally a minute. But we don't have to. Okay. The exact speed isn't important at this moment. The point is, you need less speed to be in that orbit.
Because you're gonna jump up to Leo, kind of pause for a second, and then once you've got that, it's actually really easy to make the next move.
It's easier. Yeah, but it still takes a lot of energy to go from Leo to Geo.
Because again, Leo is really close to the Earth.
Yeah.
So it's really still got. I'm gonna make up a number. 90% of its gravity. You haven't left.
You have more. You probably have more.
More than 90%. At 300 kilometers, you still have more than 90%.
That's me doing it in my head.
I know. Right.
I'll tell you pretty soon.
Not to put you on the spot, just trying to understand.
On the spot or anything.
Yeah.
Boy, oh boy. You're sending me down a rabbit hole.
Sorry, man. Sorry, Stephen.
But I love it. It's just, okay, we're going to square. Hey, you weren't far.
Okay.
You know what? It's about 90%.
Excellent. Feel good about that.
Okay, so sorry, we got sidetracked.
Yeah. No, that's so you're still at 90% ish, plus or minus, at 300 kilometers up.
Yeah, so, Geo, now you're 36,000 kilometers off the surface.
Yeah,
you're nearly 3 Earths away from the surface.
Right.
Okay. Huge.
So inverse square law means you've lost most of that.
Very small. Gravity is not negligible, but it's small. Again, I don't feel like doing the calculator but it's small.
Yeah. Remind people about low Earth orbit. How fast is it spinning around the world? And then contrast that to Geo and what those two differences mean, because the business models of those orbits are fundamentally different. The use cases are different.
Sure.
How you need to do it. The price tags are different. Everything's different.
Yeah. Okay. So I think a good number to try and remember is if you're in Geo, of course, the definition of geosynchronous,
right?
That's what Geo is short for, means you're synchronized with the spin rate of Earth. So if you're above a point on the equator and you're in orbit at Geo, the Earth and you spin at the same rate. You go around the Earth once in one day,
right?
But you stay above the same point. So if you were standing on Earth looking up at a Geo satellite, you're standing somewhere in Ecuador, I don't know, on the equator, and you're looking up, you will see that satellite above your head all the time. It'll look like it's stationary in the sky. So we call it geostationary. Geo for Earth, stationary for stationary. Anyway, so it's like synchronized with Earth. It goes around once per day, but the ISS in low Earth orbit, for example, it goes around about 16 times a day.
Yeah.
So it's covering less distance to do that. Right. One time around at low Earth orbit's a lot less than one time around up there, but it goes around. I believe it's 16 times. Gravity at geo is 0.03 Gs. I see in the comment. So so that's 1 sec 0. Well, yeah. So it's 3% of Earth. That sounds about right. Not a lot. Yeah. So you're spinning much slower when you're there. No, and I don't want this to be about space elevators, but
right, yeah.
If we had a space elevator, if we did, GEO would be a lot cheaper to access than LEO. Right now, LEO is much cheaper to access than GEO because we get there by conventional rocket.
Correct. Yeah. And you know, when Edwards and I were doing our original work, and then when Liftport came along, we're like, we will never put anything in LEO, not ever. We will not ship cargo to LEO because it's just a giant obstruction to what we're trying to do. So
I don't want to make this about space elevators, but there would be ways to do it.
Right.
It's not important.
Yeah. All right. So it's hard to get to LEO. Once you're at LEO, it's relatively easy to get to GEO. What are
by rocket? You still need to expend a lot of fuel to get to GEO, and you would need to expend yet more if you want to leave the sphere of influence of Earth.
Right.
So each of these steps require quite a bit of delta V.
Yeah.
Sorry. Continue.
Yeah. No. So that is kind of right now the primary sphere, if you will, sphere of economic influence. Most of the world is putting most of the stuff in LEO. Some things are going out to GEO. Only a very small fraction of what we put into the sky is aiming for the moon, and even less now going towards Mars. And it comes down to physics. It comes down to physics that it is just harder. Those milestones become harder, more expensive, more challenging, more complicated, more radiation, more time, more money, more everything to get to those expanded destinations. So talk about, there's folks that want to talk about, full-scale settlement of the moon and Mars. Let's put your physics hat on. Yeah. We're not going to talk about radiation. We're not going to talk about terraforming. We're not talking about engineering, right? I'm not.
Yeah.
But what makes it more? What makes one destination more challenging than the other from a physics perspective?
I think it's fun to really picture interplanetary motion. I think you're talking about going to Mars. It's interplanetary motion.
Yeah.
So I think it's good to kind of understand the various phases to that mission. So an interplanetary mission, its destination, let's use Mars as an example. You know where the planets are at all times. That's easy. So whenever you decide to leave Earth, you know where Mars will be when you would eventually get there, but actually it depends the exact path you take to get there, right? So there is a neat dance just in the kinematics of it, in where are we going to be when? But what are the various impulses we need and when are we going to do them? So first you're just going to get to orbit, and that takes a huge amount of fuel. Because we should probably mention how rockets work. I'm sure most people have a good idea if you're watching a space show, but it's so counterintuitive. If you really think about how a rocket works, I mean, it's ridiculous. I'll give you an example. When I was, I grew up in the 80s, and Batman 1 came out, and you'd see the Batmobile and you see the fire coming out the back. And my thought, because I was young and not an engineer yet, I thought, well, I guess it's shooting fire out the back. It's shooting something out the back, and that's what makes it go forward. Kind of like if I would stand on a skating rink and throw a medicine ball that way, I would slide the other way just to change a momentum kind of thing. However, of course, no car works that way. That would be stupid. You should use the road. You should push off the road.
Right.
And if you do that, you can exert a force on yourself. It's much better than throwing mass out the back. But rockets have no other option.
Right.
The moment they leave the atmosphere, they have nothing to push off of. And if you can't push off anything, you can't have an F, and you can't have an F, you can't have an A. Don't have an A, you can't change your V. So that's why rockets work the way they work. But it takes a tremendous amount of fuel to get up into orbit. So if you're going into geo, just let's say that was your final destination, 90% of the mass that is sitting on the launch pad before it takes off is liquid fuel. That's what it is. Right. 10% is everything else,
right,
including the canisters that held said fuel. And so on.
Let me just. I want to fact check myself. This is how I describe it. 90% of it is the fuel. 8% of it is the box the fuel comes in, which everyone else calls a rocket, and then the last 2%, 3% that's left is the actual cargo you want to get into space.
I think you have less than 2 to 3% that's cargo. Okay. It depends how far you're going.
Yeah,
but ultimately 1% is not unusual for that's the thing you're trying to deliver, and it's unbelievable, right? Who would design such a thing?
I had a conversation with my mom. She's very religious. I'm just going to put that out there. And we were having a conversation about her beliefs. And I'm like, it's kind of miraculous that we can get to space at all. Because if our world was just a tiniest bit bigger, the rocket equation wouldn't work anymore. Right? Am I right about that? Just a little bit bigger, and the rocket equation.
Oh, you mean more massive?
If the world was a little bit more massive, the rocket equation wouldn't work.
No, the rocket equation wouldn't change.
Well, okay, but we wouldn't be able to get to space. The equation would still be true, but we don't have enough current firepower to get to orbit.
Well, there would eventually be a limit with conventional rockets. Yeah.
It was an interesting conversation. I mean, my mom's a pretty interesting gal, so hats off to her. But it was I was trying to describe like just how kind of cosmically lucky we are that we can even get to space at all with rockets. So yeah, cool, neat.
There's a question, but maybe we'll get to Mars first.
Yeah,
because we started our trip to Mars. Once we're in orbit, because we've exhausted all that fuel and now we're just falling around Earth, then at the right moment, we're going to shoot a whole bunch more fuel to increase our velocity. And at different altitudes, so whatever altitude you're at, there's a certain velocity you would need to have in order to leave the sphere of influence of Earth. And now you're on to your next point, which is to orbit the sun.
Right.
Because
you're still in the solar system. The sun has giant pull on you.
If you expand out and look at the situation from a solar system point of view, you would see we're really close to Earth still.
Right.
But the sun is 300,000 times more massive or so. And so you're quickly orbiting the sun. And once you're doing that, Earth's playing a small role, and soon it's playing zero role. And now you're just orbiting the sun at some fairly high speed, but you're going distances that we would refer to as astronautical units. That's the kind of distances you're trying to cover now. That's, and at one astronautical.
An AU is the distance from here to the sun, correct?
That's right. It's 150 million kilometers. So we're talking about going such huge distances. Anyway, eventually you link up with Mars, but you're not going to want to crash land on Mars at those speeds. So you now want to slow down in order to be captured by Mars's gravity, by Martian gravity. And now it's sort of the reverse problem. As when you were leaving Earth. Now you're leaving the sphere of influence of sun and entering Mars's, However, be careful or you're just going to shoot around it. So you need to slow down. And unfortunately, slowing down is no easier than speeding up because there's nothing to break in. I mean, yes, you will eventually encounter atmosphere, but you can't do that at kilometers per second because, well, yeah, that would just be too much of a bombardment of atmosphere. I suppose every planet's different. Every planet has its unique atmosphere, but there's really no atmosphere you want to enter at thousands of meters per second. Anyway, and yeah, now you could do some aero braking, it's called, where you do slow down as you enter the atmosphere. And then you touch down. Now you're flying in some kind of atmosphere. We know how to do that. Basically, well, if you can get from our launch pad to the atmosphere of Mars, I suppose you can figure out the rest. So those are the various steps. It involved really 3 big moves: a big impulse to leave Earth, a big impulse to orbit the sun, a big impulse to slow down, and now you're falling onto Mars.
At what point does your relationship to Mars overwhelm your relationship to the sun?
So every
does that
planet,
matter? Is that a dumb question? It feels like a little like a dumb question.
No. So Mars, the Martian sphere of influence, should be a little less than Earth's. That's it, because it has less mass. It's smaller with less mass. The equation's sitting in my orbital mechanics textbook, but it's quite close to those planets, relatively speaking, to the sun. And the thing to have in your mind is, again, 2 masses fighting over you. When does one dominate the other? It's not so different from the idea of that Lagrange point.
Right. There's no Lagrange between the Earth and the sun because they're not there. The sun has. I'm sorry, I'm saying this wrong. There's no Lagrange between Mars and Earth.
Oh, that's absolutely true.
Yeah. There's Lagranges between Mars and the sun, Earth and the sun, Earth and the moon, Mars and its moons.
Yeah. Every body has its boss.
Yeah.
And if you're so yeah, our boss is the sun. Yeah.
Okay. Don't we all? Everybody has a boss. No, that's really cool. I had not really thought about it. All right, so there's 3 maneuvers you have to 3 maneuvers you have to take to get to Mars, plus or minus, and it's pretty similar to going to the moon, right? Like maybe the distances aren't as extreme, but you still have maybe the sun doesn't influence you.
That's right. No, that's right. So there's 1 step less to get to the moon. It's called a Hohmann transfer, but you are going to orbit the Earth, and then you're just going to do 1 big shot, and then the next adjustment is orbiting the moon. So the number of big delta V's are actually the same, but they're smaller. It's still a 3-step maneuver, really.
Do you know who Hohmann is?
Oh, I don't know his first name.
Okay, all right. I mean, try to, maybe he's not quite as big a deal as Newton, but
right. I'm sure, I'm sure his mom was proud of him, but I don't know. I don't know his first name.
Okay, all right. Okay, so all of this is about energy. All the business plans that I want to support people on ultimately comes down to, do I have it right? F equals M times A?
Well, so that's at every instant what acceleration you're getting.
Right. Yep.
You want to talk about energy.
Okay.
That's also an important framework to consider. Now you're just comparing any 2 points in space, and you could say they're at different energy potentials, different potential energies. And
okay, so I've never understood the energy potential piece. So I was kind of with you most of this.
This one Okay, so this is very basic.
So we have 10 minutes.
Oh, energy in 10 minutes? I don't know if we can really do it justice.
Okay.
Basically, if you want to change the energy of something, you have to do something called work. And work is an accumulation of force, really. You can't do work at an instant. just like, so in order to change the amount of energy a system has, you need to do work onto it.
Okay.
And the more work you do, the more energy the system has. But the form of energy, the mechanical energies we deal with in space are really potential energy associated with gravity, and kinetic energy that's associated with how fast you're going. But the sum of those two things, if it's to change, you'll need something to do work onto you. And why not a chemical rocket? So that is exerting force, yes, that gives you an acceleration at any given instant, yes, but it's the accumulation of that force while you're moving that is changing your energy, how much energy you have. But depending which way you're moving in the gravity field, that'll really determine how much of it goes towards your kinetic energy, the energy associated with your motion, or how much of it is just you escaping the gravity well, but you're not going any faster. In fact, you might be going slower, but you still required work to do that.
Okay.
Anyway, we're covering big chapters of physics in short time. So
right. Okay.
Doug has a question.
Doug, what's your question?
It says, would you care to describe gravity losses for a rocket? I think that's right. Do you see that? I see that. Okay.
Yep.
Yeah. So it's really, if I understand the question right, eventually things in low Earth orbit could lose altitude. It could take a while, but even in the lower atmosphere, you eventually, even when you're just outside the atmosphere, you're still going to eventually collide with small particles, and they might slow you down by a fraction of a meter per second, but over time that adds up. So even though we described a satellite as a rock falling around a planet, it is a rock with fuel and engines. It needs to fire sometimes, to maintain altitude, but also to adjust attitude. Attitude is not just your speed and position of some point on it, it's which way you're facing. And to change which way you're facing, that requires multiple shots of fuel to rotate you. So there are still small needs for fuel when you're happily in orbit.
Awesome.
And we have the German Walter Hohmann is his name. Okay.
Thank you, Dr. Plata. I appreciate that.
We have a great fact checker on board here. This is awesome.
Dr. Plata is no joke. He knows his stuff. He's pretty cool. Leah just posted, Doug is amazing, and he is. We like Doug a lot. Okay, I'm going to ask a question that I do know the answer to, but I want to use it. It's a dumb question. It's a dumb question from armchair physicists.
Mm-hmm.
It gets on my nerves. I've been fielding it for 20 years now, but I want you to understand that lots of people think they know physics and don't, which is one of the reasons why you're on our show. It's one of the reasons why we're talking about getting physics and why I'm going to recommend this book. But people ask, for the space elevator, imagine a tube like a straw.
Mm-hmm.
Why can't you build a straw to space and let the gravity, the vacuum of space pull a capsule out to space? I've been getting this question for 20 years.
Well, I've been teaching for not quite that long, but I've certainly been in 20 years of classrooms that involve physics and engineering, and I've never heard that one.
You have not spent 20 years reading the trolls' comments on
no, thankfully.
Right.
Thankfully not.
So that's a real question, and it comes up shockingly commonly. It's
okay.
It's shockingly common question.
So first of all, would a vacuum, things get pushed from higher pressure to low pressure. And so what you're suggesting is if you would have a vacuum far away.
Space is a vacuum. That's where they're coming from.
Yeah. And you have a long straw, and it's going into our atmosphere, where there's 1 atmosphere of pressure here, 0 atmospheres of pressure there. Okay. Well, there's a huge distance to cover between here and there, for one. But okay, let's argue that you could somehow have a 300-kilometer long straw, or
Right.
that's okay.
Yep. Yep.
And somehow it's being held there by forces unknown.
Magic.
And now, if you could do that, could you just place something at the bottom and the vacuum up there will bring it? Well, theoretically, you wouldn't have an instant change in pressure. It's a gradual change in pressure. So if you have 1 atmosphere down here and 0 atmosphere on one end of the straw, and you have a continuum there, it's not like right here I have 0 pressure. It's way down there.
Yeah.
What causes a force to manifest is a change in pressure, but you would need a change in pressure on 2 sides of that body. So let's now extend ourselves and say, okay, no, that body is really plugging this straw so that eventually it's actually a pure vacuum on the other side.
Right. But the gravity of the Earth holds the atmosphere down. So you can't get the vacuum that they're hoping for. Right. Like I'm telling you, read the trolls comments. Read the trolls comments.
All I'll say is arguing against the possibility of having a straw from atmosphere to vacuum is not as easy as most of the arguments I usually take on. Not arguments, but most of the descriptions one would take on, because there might be a scenario where you could have an upward force because of pressure gradient that goes against that fights the gravitational pull. There might be. Okay. This is the first time I'm hearing of it. But I think the efforts to assemble such a thing are probably harder than any space elevator of any kind.
That's where they were like, hey, build an elevator. Like, anyway, it's a crazy story. There's a whole bunch of stuff there, but it's been out there for 20 years as an alternative to a space elevator.
To Doug's point about the helium balloon, it wouldn't get too far because pretty soon the atmosphere thins out and the helium won't help you.
Exactly. Yeah. All right, but that's the kind of stuff that I've been dealing with for 20 years, is that people don't understand the basic concepts that physics determines everything that we do in space. It's the starting point, long before policy, long before nations wanting to launch Sputniks or missiles, long before ComSats and GPS. It starts with physics. So, Professor, I really am grateful that you came on to our show. We're going to post the book title one more time there. Thanks, Leah. Appreciate that. Please check it out. It looks really interesting. I haven't gotten my copy yet, but I think it's on its way. And with that, we're gonna close off. Thanks a lot, Professor. It's really fascinating talking to you. We'd love to have you back. I want to remind everybody that we've got a conference coming up at the end of March at DareGreatly.space. And please keep coming back to our shows, because I think they're fascinating, and I think you all think they're fascinating too. So we've got a great guest with Dr. Ressler coming in on Monday, and we're going to do a policy show. I know some of you don't like those policy shows. I like the policy shows. Space policy is really important. That's what we're going to do next Wednesday. We're going to take we have a holiday in the United States on the 20th. We're going to take the 20th off, and we'll be back on the 22nd. All right. With that, we're out. Thank you very much, y'all. Appreciate it, Stephen. Take a look at the book. Thanks a lot, sir. Appreciate it. Bye-bye.
My pleasure.